So this week we are covering this recent paper called Leave No Context Behind, Efficient Infinite Context Transformers with Infini-attention. So the title of this paper is very catchy, the idea of that Infini-attention, so that we can remember everything that we want to about the text and we can just process very long sequences. So the paper is sort of adding like an associative memory. We will discuss that. And it is trying to save things that I think it will be helpful for the model for certain tasks, and it is trying to retrieve them at later time. Not exactly at the later time. We'll discuss the flow in much more detail, but the idea is that they are using an associative memory here, and this series of paper comes out of the idea of like how really do we process long sequences, and we discussed something related to this. I think 1 year or 2 year back when we tested. We talked about this paper called Alibi, which was about train short and test long. And so this is a interesting side. The idea is that uh, currently the transformer architecture, it has the n square complexity, memory complexity and computational complexity because of the this particular matrix that we have to create. And the thing is that people are trying, because of this n square complexity, we can't really put very long sequences through for our models because that would require a lot of memory. There have been advancements like flash attention, and we are now seeing models which are, up to 32K and 128K sequence length, maximum sequence length. But yeah, the paper seemed like it would be you can remember as long as you want, and they only show performance on two major tasks, which we'll discuss later. Okay, so yeah, we know that uh, sorry, the attention mechanism is quadratic complexity in both memory and computation time, and people have been trying to come up with solutions that might avoid this n square complexity, and that is where Henry, what you were discussing about, right? And linear attention comes into mind. That people have been trying to implement or at least approximate the the attention values that we get from this equation using some sort of a linear method. So the attention matrix that is created here, they're trying to come up with a solution, a linear solution, so that they can approximate this part of the equation. And so if it is since if it is linear, that would bring down the complexity of these attention mechanisms from n square to n. But the issue comes here because of this nonlinearity, softmax. So because of this nonlinearity, it is not even like you can apply this nonlinearity to a smaller part um, of this matrix, because this matrix is basically telling like in what sentence which token is more important, and it's like a relative measure for each sequence. So that is why it is important to put the softness on the entire sequence. And people have tried to approximate this part through different methods, but I think they have not been that successful till now. So basically, the authors claim that they introduce a novel approach that enables transformer LLMs to effectively process infinitely long inputs with bounded memory footprint and computation. So the idea is that their memory does not depend on the sequence length. It is a parameter of the model dimensions and the dimensions of the key and value vector, which we will see how that happens. And the idea is that they don't have to like in some models like Transformer XL, the length of the segment or the total length becomes a parameter for the memory that is used by the memory component that was added to the model. But they're saying that they have a bounded memory footprint in computation. Okay, so the gist of the paper is that they store old KV states of the attention in a compressive memory, and instead of discarding them like the standard attention mechanisms. So what that means is that in this equation, if you see, once this A dot, just like this attention value that is created, right? Once this is done, it is discarded at each level. Yeah, so this is not further usable in, let's say, in the next layer or the for the next token prediction. So they are saying that they are trying to save information that can be leveraged later, and particularly they are focusing on the KV states, and we will see why they are focusing on the KV states later. And to test their performance, they are focusing on two major tasks. One is the passkey retrieval, in which one particular key is like stored in the middle of a very huge text, and the idea is that you have to retrieve that passkey from the given input context, and this is tested in both zero shot setting and a fine tune setting. So if it is, the model is able to do very good on even on a zero shot setting for passkey retrieval, that actually means that it actually works on very long sequences. And the other one they are trying focusing on is a book summarization task. And so the context length for these tasks is usually around 500 and K tokens. So these are the two tasks that they focus on. So just to quickly revise on the traditional scaled dot product attention, which was introduced in the original paper Vaswani et al. In 2017. So yeah, first we'll talk about single head implementation, and then we'll talk about the multi-headed implementation later. So basically for an input, uh, you input X of dimension n into D model, and is the sequence length. We first compute the key, value, and query vectors. So the idea, it is basically these values are calculated from the same initial input vector, and they are converted into specific representation using these WQ, WV, and WK vector. And as per our understanding, these Q vectors are like a query, like something like, let's say for a particular task, you want to search or find something that might be relevant for a particular task, and then using these Q values, you find that measure of what part of the input is most important for this particular task using by multiplying these query with the key values. And after that, we implement a softmax on top of that, so that gives us like a normalized result of, okay, in this particular sentence, this particular token is like much more important rather than the other rest of the tokens. So once we have a multiplication of those, we multiply them with the value vector, and value is also like the input shaped converted into a specific form, and that basically gives us the attention values that have been traditionally used in the transformer model. And the idea is that you, based on whatever task at hand that you have in training, you are basically extracting the most relevant information from your input by calculating these these by figuring out these values which show what part of the text is important, and then taking out those parts from the text itself. So here in the paper, they have called uh, this original attention method as the A dot. And whenever this is done in a multi-head setting, the same operation happens in different let's say if we have 8 heads, the same operation will happen in eight different places, and the result is finally concatenated and further multiplied by a vector, so that there is some sort of a learning also if there are multiple heads involved in the calculation. So after that, the authors, they introduce their idea, and to understand this, we will basically start with the end point, like what they do at last. So A dot is the equation, is the result of the original the original attention mechanism that they have. So basically, and A memory is the representative, is like the attention value that they are calculating, and this is like a gated sum of basically gated sum of the original attention method and the whatever attention values they are calculating from the memory that they have saved. So basically it is yeah, and the beta parameter is a learnable parameter which they figure out during training, and the idea is that whatever output goes uh, from from a particular layer, it will either be a dot or a memory, or some sort of a combination of, let's say, point 0.6 a memory and point 0.4 a dot. So the representation which is passed to the next layer can be completely from the memory, or can be completely from the original attention implementation, or could be a mix of something from the memory and the original attention mechanism. So this is how the information is passed after retrieving something from the memory. Now let's see how they calculate their memory. And so their memory, this is their memory, and this is their normalization constant. So at any point, what they're doing is they're updating their memory by adding this value to their memory. So they are adding this kt k sorry this nonlinearity applied on the transpose of the k values, and multiplied by the v vector. So this is, I think, an outer product, and which basically would give you a matrix of value of d key times d value. And yeah, so as they said earlier, they're trying to save the k and the kv values of the that are calculated here, for the original dot product. They're trying to save that, and at each step they are saving this representation of kv value, and this is a normalization constant which is basically uh, updated after each time, after each step, and it is basically the sum of all the terms after applying the nonlinearity on the k values. Now, I know this is a bit confusing, but just bear with me. So now let's see how they're calculating the A memory. So now you see the the thing that they are finally calculating and passing on to the next layer. It is calculated by applying nonlinearity on the q vector multiplied by the memory at the last step. So if you see what is happening here, it is basically non-linearity on the q vector and non-linearity on the k transpose times v. So what they are trying to do is basically approximate this part. So if you see here, there is a multiplication of q, k transpose, and v, and here also indirectly what they end up doing is a multiplication of q, k transpose, and v. The only difference is that here for non-linearity they apply the non-linearity on the multiplication of q and k transpose. Here the non-linearity is applied separately on the q vector and on the k vector. So what they're trying to do indirectly is they're trying to save the approximate result of the attention matrices that were calculated, the result from this attention operation that were done, let's say, some time ago. So they're trying to save an approximation of this value. So um, I hope that's clear. Any questions till now? Okay. So when even when I read the title of this paper, it seemed like they would be saving something about the input or something about the information that they find while computation or something that would be retrieved later. But the paper is indirectly trying to save the approximate value of the attention operation. So yeah, and to update their memories, they are not directly, sorry, they're not directly doing this here, this operation. They are doing something like the delta rule. So the idea is that they update only those values that need to be updated. Like if some particular information is already present in the memory that they have, they would not rather not update it and let it be. Um, I don't understand what exactly happened here, but that is the idea behind is that only update what is necessary, what does not exist in the memory already. And in the multi-headed setup, we calculate these A values. So this A memory is calculated for each and every head separately, and then it is concatenated, and in the end, it is multiplied by a learnable matrix. So yeah, um, and the idea is that they're not really trying to, and they're and also this thing is not. I'm not sure if it is trainable or not because key and this k and v vectors are coming after multiplication for by wk and wv. But yeah, the idea is that whatever we are saving here, it's like they are just trying to remember what past computations that they have done. Like if they had a similar vector and similar vector that came earlier, they're just trying to look back into the memory and seeing, okay, have we done this computation earlier? If yes, they use whatever is saved in the memory for yeah, you use that, and yeah, you and try to get the same results. And the thing is that they are not exactly saving the exact attention operation that was happened there. They're trying to save like something quite which is quite similar to it. And yeah, so now the memory requirement for this is this thing. The memory, so the memory footprint of this model is D key into D value. And for this normalization constant, it is, since it only involves the uh, key vector, it is D key into D value plus D key. And this is, yeah, and this will be done at each layer and at each segment of the text. So yeah, that is what they mean by that. They have a bounded memory footprint, and it does not directly depend on the length of the vector that is being processed by the model. And talking about this figure, so this figure here shows the results of the gating score. So if you see that, let's say this is, you can think of this, that this row is for the layer 0, And if they had eight attention heads, what was the gating score for each of those heads? So when a gating score of okay, so the gating score uh, is either is between the value of 0 or 1, and if it is when it is 0.5, it is taking both the stuff from memory and from the attention value that we calculated at that particular layer. And let's say if when it is zero point 0.8, when it is zero point 0.8, then it is taking most of the time, it is taking from memory, and like zero point 0.8 times it is taking from the memory, and zero point 0.2 times it is taking from the original attention implementation. Another interesting thing that the authors pointed out was that at each layer you will see at least 100 value for this gating score, which shows that if it wasn't zero, it would basically mean that the back propagation would not happen, because the path would stop going. The path would go through the memory that they have created. So I think for the model by itself, to make sure that the model is learnable, and since the value beta is also trainable, it is a natural occurrence that is happening, that at least in each, at least in one of the head, it is taking the results purely from the for the vanilla, using the vanilla attention implementation. And I will quickly discuss the results of this paper. So this is the performance of the model for the pass key text, for which basically has to retrieve a particular value hidden in the text for up to 1 million context. If you see here the this particular model, the three slashes here show where the text was hidden. So the first slash here shows the if when the text was hidden in the earlier part of the text, and in the middle and at the end. So you can see whenever the passkey is at the end, the model retrieval performance is very nice, because it is in recent context, so the model will perform better. And when it is in the earlier parts of the context, the zero shot performance is not good. But the authors claim that even after with just after 400 steps of fine tuning, they are able to get these very good performance for this particular test. And talking about the book summarization task, uh, um, so they basically establish a new SOTA on the book sum task here. And I don't know why they only compare with BART and these particular models. They might have gone with other models also. I think they're just trying to compare with encoder decoder models. But yeah, they get a new SOTA on this particular task. And another interesting thing that was there in this paper was that they're saying that the more text, the more input length that you for the summarization task, the more input length that they gave to the model, the Rouge score of the model kept on increasing with that for the generated summary. So I think they're just trying to highlight that they work better even with more context in their input, rather than their quality of the summary degrading because of more input text present in the context. And yeah, this is pretty much it. And yeah, so again, the title of the paper was very interesting, but they don't show much about. They didn't test it on many more tasks, which would have like definitely showed that this thing is actually working. And they are not trying to, uh, because it is not a memory, it's just like a lookup of the past computation. So yeah, that's it from my side. Any questions?